So today we're going to go through some of the working problems assignment 2. Just as a quick note, this was the please go try it part of it. This was just an attempt to go through practice using a certain data set, reformatting your concentration data set over to a capacity input file, taking the capacity input file, build a capacity model, do your parameter estimation. So if you had any problems with this, please do flag it. I'd like to know if, I want you guys to be able to actually execute this point. So this was just a series of different ones where we were going through and asking you to try those 3 different possible models with the sets that you have. So in the end, you should have a series of different capacity files for each ones you've tried through. If you want, send me your capacity file. I can possibly look at it and do an edit. And same thing for your input files. Most of the times, the problems I see with this, and I saw it with some of the ones that you handed in, usually it's syntax. There's something that how you refer to a certain step incorrectly. Your initial concentration may not be set. There's these small little features. And again, it's usually something I can work through if you just shoot me your file. What we'll talk through is mainly sort of the applications through here. So 3 steps. One is applying and using sort of the VTNA template. Second is assuming that template, go build a model that matches this mechanism. So this is parameter estimation again to say, does the data you have match against this assumption? So this is really just a test to say, you believe this is the mechanism. Can you fit it back to that as a real fit? And then finally, what you should have found is it doesn't. This was something we discussed in class, that the model that we're presenting here is too simple, and in fact you have to modify your mechanism. So the goal here is to say, in this normal sequence of you ran a reaction with a certain set of assumptions, you've done some initial rate sort of understanding, you're testing to see if your mechanism holds up, and when it doesn't, how do you go back and change this to match? And I want to give you some pointers in terms of looking at the data to help guide you along that. So for the first one, your order in A could have been pulled from a couple different experiments, but usually focusing on 1 versus 2, where your concentration of your catalyst, your concentration of your initial concentration of B is the same, and your concentration of A is the only thing that's varied. This is what you can put into your template. So what I'm showing here is it's from the slide that says you're trying to solve for the order in A while you're looking at what the product trend is actually doing. And using that, what you guys should have found is 1 is not too bad, somewhere like 1.1, 1.2. And again, I'm making that call by saying I'm trying to get these data points right here to kind of coincide with each other. Now, first point of conversation, the way that the template was actually set up, you could solve for the order in any component using any of the other data trends. What I mean is there is a sheet, or one of the sheets in that Excel template, where you are using the product trends solving for order in A. You can also use the B trend solving for the order in A and vice versa, right? You can basically look at any either consumption trend where something is changing or a product trend. So in this case, I'm focusing on product. Just as a quick, this is something that came up and some people asked, which do you use? In other words, is it better to say, I am looking at the relative change in B, so the consumption of B, and comparing those two in order to solve for what happened or the order in A. In other words, you could actually, in this case, plot these 2 experiments focusing on B consumption over time, so you'd have 2. And in the same way, you're doing a time adjustment because of this change in A concentration to extract an order in A, right? But open thoughts. What do you guys think about that? Like, what is the advantage, disadvantage, or sort of caution of focusing on, I will watch the product trend in order to extract an order versus I will focus on a starting material trend to extract an order?
If there's a side product, then your starting material trend is going to give a different result than your product trend.
Yeah, saying it another way, remember, consumption of B, you're saying the rate of disappearance of B versus production of product, rate of appearance of product. If we assume consumption of B, so minus dB dt, equals production positive dP dt, it doesn't matter, right? If we know that all material comes in and out, that's fine. But yes, an intermediate, if B goes to an intermediate and then product, that might dramatically impact your conclusions. Or if B goes on to 2 different products, then that might impact your conclusions. Yeah, that's right. What else?
I was going with like a mass balance.
Same argument, right? If you're basically saying that you can't watch all of the starting material consumption and that doesn't immediately track to your product, you just have to be aware of it. They mean different things, and sometimes they're very valuable. In this case, what we're trying to say is if I screw around with the concentration of A, how does that immediately impact how fast product is being formed? If you had something like a selectivity question, B is going to more than one product, then sometimes changing A and how that impacts how fast B is consumed could tell you about a second reaction where A and B react with each other to form something else that's not this product, for example, right? So they can be meaningful, but it's just a caution that basically you want to kind of repeat to yourself what you're actually solving. In this particular way, this is the most pedantic one of I am changing a starting material and I'm looking for the final outcome of a product. And usually as long as it's a single starting material to a single product, this is fully appropriate. When it gets complicated is when you have different species. Okay, so here is taking two different ones, also trying to solve for order in A. So in this case, I'm actually taking, like if you go down the list, we have also this one and this one where B doesn't change, this one where A does, and the two concentrations of catalyst are the same. So if I take 3 and 5, this is the graph I would get looking at the product. Thoughts? Good, bad, other, complexity? Why? Why I see negative? Why?
It's not enough data points to properly assess the line.
Yeah, this is a function of the sampling rate that you have, so how fast you're sampling. It just happens that you have in this larger concentration one, so this experiment number 3, you have one data point here, you have one data point there. And then you're sort of mentally interpolating between the two that is probably linear, but you don't know. The entire data series you have for this lower concentration is actually contained in that kind of range. If this is all you've got, you could sort of say, whatever. Not best practice is basically the point. So this comes to the thing that we discussed in class about if you're going to make these perturbations where I'm changing some initial concentration, generally small changes, 10 to 15%, are best practice because that means that we're only doing a small perturbation rather than these large jumps. It may entirely be, it may not matter that much, but this is kind of approaching that extreme change in concentration where you may be influencing other things you didn't intend to. So I'd say that generally you shouldn't use this one, or at least drawing data from this one is very suspect. Okay, going over to B. So here, this is where we discussed this before. Here is a good pairing where the catalyst concentration doesn't change, B does change, but we're not left with a perfect unity here. And you have two choices. You could say, look, it's close enough that 0.1 versus 0.11. You also know that the order in A is first order, so you could just move forward and say, I believe any small changes I'm seeing may be because of the nascent order in A, and go from there. So this is the plot of product versus time, trying to solve for order in B, where I've set the order of B equals to 0, and that's a pretty decent fit. Like again, any small perturbation I'm seeing around this one, it'd be reasonable to assume that if it doesn't perfectly overlap with each other, experimental noise or the small change in concentration A, which has an order in that case. If you guys wanted, the other thing you can do, if you check through on the Excel template, instead of doing these single component concentrations, there's a tab at the very end called KOBS. If you remember in Jordy's paper, you can do these one-by-one concentration solves like we're doing over here, but you could also take every product curve that we have, all 5 experiments. You can actually populate all 5, and you can solve where the time axis is both A, B, and catalyst. So it becomes an aggregate sum of every one of the different species you're changing. It's a more complex setup, but you could potentially fit multiple parameters. So the other way to do this is to set up a new tab where instead of just being time normalized by B, it would be time normalized by A and B, where you set A equal to 1 and B equal to 0 in order to solve for those two pieces. That's another way to deal with this where you're actually doing multiple manipulations. But that's possible. The last one is order and catalyst. So here I chose these two. And if you set order of catalyst to 1, reasonable overlap over here, but you notice they start to deviate at this high point over here. Okay, so what, again, in your own words, what is this? This should kind of worry you a little bit. What's going on? What's that?
Got saturated.
Got saturated. What do you mean?
Zero order.
No, I don't think so. So remember, if you look at the two experiments, we're currently comparing the product curves. So this is product over time for that experiment and that experiment. In other words, we're starting with the identical concentration of A, identical concentration of B. The only thing we changed is that one has a higher catalyst loading. This is a lower catalyst loading. What is the yield of these two reactions? If you look at that one, yield of red versus yield of orange, which one's higher? Orange. I made more product with orange than I did with red, right? If these are identical reactions and all you changed was catalyst, yield should not change, right? If yield is changing, there's a big problem here. You're not reaching the same degree of conversion for all sorts of practical reasons, but remember, first principle says, if all I changed was catalyst, I should just get to my product faster. I shouldn't have less product. I just got the product faster. That right there, if all you did was change the amount of catalyst and how far the reaction gets is not the same, that is a giant flashing light that you have catalyst deactivation somehow. And if you add more catalyst and get more product, it means the catalyst is dying probably through the course of the reaction, or your product is inhibiting the catalyst. So having more catalyst in the system helps you to push forward the system faster. This is if all you did was everything is identical, like these two, and that's what you see, it has to be you're hurting the catalyst somewhere. Something is going on that you do not reach the same degree of conversion. Something has to go on. Could be atmosphere, could be solvent, could be impurity, but that's the thing that should be really bugging you. It does mean that at least initially, it is first order in catalyst. When the two guys start off, this is probably a first order system. The deviation you're seeing is just that when I have lower catalyst, like in this experiment here, I'm just not getting as far. So what I'm probably seeing is something where if I was to plot the concentration of catalyst against time, in one case it starts here and it is dying, and the point where there's no more conversion, I'm probably getting here the concentration of catalyst, I'm going to assume equals 0 at that point, which is why I get no more turnover. That there's still starting material present, but basically I've got some kind of a component. Now I don't know if it's a linear first order decay, I don't know if it's exponential, but there's actually a third paper Jordy put out if you want to look through this. You can use the VTNA method to help to correct for this, because all we're saying here is the Tcat, we're assuming time is multiplied by catalyst raised to some power where catalyst is a constant. I can say that catalyst is changing. I can put a function on it and say I started with a certain amount of catalyst. I'm going to draw a straight line saying it's dropping over some period of time. Maybe it's a zero order decay. And then you can make an assumption of how much catalyst you might have by just creating a new column of how much catalyst over time you have, assuming some degree of deactivation. Then you can play around with how fast it deactivates to see if you can correct for this function, right? So it's just the big number one jump is you do not see conversion matching as you change catalyst, something's deactivating. If you can match the rates first order like this, it's probably not this rapid initial deactivation, it's just slow deactivation over time, is usually what you're seeing. This is where you can step back, and what we're talking now is kind of these, stepping to kind of sample 2. If you look at 2 experiments, so these are all 3 curves, starting material A, starting material B, and product for those 2 experiments that we've been talking through, right? That's these 2 right here. Where the one that's reaching higher conversion faster, that's your experiment number 4. The one that's a little bit more shallow, that's experiment number 3. And there's, again, this is where you can look at all the different curves and say there's something that doesn't quite match up. You can see the product formation and the starting material B, the blue one, no, not B, A, excuse me. Yeah, starting material A for these 2, their shapes pretty closely match your product shape. So the consumption of A and the production of product, that is sort of a stoichiometry match in that case. Using up less A gets less product, that's good. That's matching this kind of step. The thing that should jump out we mentioned before is that even at a time where conversion stops, B is still decreasing. So dB dt does not equal to 0 when dA dt equals 0. This goes back to mass balance. What we're saying is the rate of consumption of B and the rate of consumption of A do not match each other, and that the consequence is mass balance won't show up, or your curves don't make sense in this way too. There's another feature too, you can look at these graphs that might jump out at you. So look at the lines here. We said B is going down when nothing else is. Okay, so B is turning to something else. What else? Look, there should be something kind of sus there too. Look at the slope of B after this part here. Same, different? Very similar. More importantly, shape, it is a straight line. Straight line change in concentration is what kind of an order process? Basically what we're saying is B is dying and it has nothing to do with the concentration of B, it's just time. B is dying over time, so you have something that says B equals dead, right? It's just a K. So in this here, it's a slow concentration. It's maybe first order in B, but it looks like it's just this linear process where B is dying at some fixed rate. Yeah?
Does the slopes being similar also indicate that catalyst deactivation and B are not necessarily linked processes because you have a change in catalyst concentration but no change?
Good point, exactly.
B dying?
Exactly. You change this, and those two lines are parallel to each other, not necessarily related to each other. So yeah, B is dying irrespective of catalyst. It's just doing its thing. You change the concentration of catalyst, and that didn't really suddenly impact, like the only reason one's lower than something else is you ate more B before this process really took over as a major component. That's also true. One more thing too. Look at the concentration difference between the two, but also let's say right here, we're kind of done productive reactions at about that point, right here. So I'm going to take a note of how much of that B I have at this point and look towards the end of the reaction. So I'm saying if I sort of go from here and I drop down to there, if you kind of read that off, that looks like, if I was going to read this off, again, you go to the numbers, 0.12 is the concentration of B, at which point the productive reaction is done. And by the end of this reaction, we've dropped down below 0.1. So at the actual T equals end, the concentration of B is now somewhere down like 0.09, right? That difference is pretty big, right? You're losing 0.03 molar or so. What's the concentration of catalyst we have in this system?
Less than that?
Much, much, much less. It means that we know B is dying. To your point, changing catalyst concentration gives me parallel lines. Probably catalyst isn't the thing that's doing this, right? Because if we had more catalyst and it was a catalyzed decomposition, we should see some sort of a difference in slope. But the last thing too is it's probably not stoichiometric deactivation of my catalyst. B isn't just reacting with catalyst and turning to poop. Because if that was true, when I'm out of catalyst, none of this should happen anymore. And the concentration swing in B that we're doing is way bigger than the amount of catalyst in the system. So it's not logical to say, whatever this deactivation is B times catalyst, right? It's B doing something and then going on from there. And again, this is not single only. These are just sort of features that I'm pulling out. Yep.
Do we know for sure that it actually is 0th order in decomposition?
No, you're right. It's not, what I mean is, during the region of time we have here, it looks like it's just humming along. Now, obviously, if we had a reaction that was B becomes dead, that's just B times K. That must be first order in B. It's just that whatever the K value we have and the range of concentration we have here, we're in that linear portion of the curve, right? It's a slow enough K that it matters, but it's not so fast that there's a lot of curvature to it, put it that way. It's acting pseudo-zero order, right? Make sense? All of these things are kind of the tricks of the trade. They're things that you do after you've run enough of these, but these are also ways to extract. You probably have all run certain chemistries like this. Maybe your data fidelity isn't so high, but you've got these different sort of visualizations of starting material, middle, and product. Even if you don't have quite as high of a data frequency, you've probably seen things like this. And the things I want to encourage you is trust your gut. If you have a system where you changed only catalyst and the reactions have very, very different turnover, there's got to be a catalyst deactivation. It's not you. You did not set it up differently. No, one made it further because it made it further before all your catalysts died compared to something else, right? You should kind of say it to yourself in the way that at this point in time right here, I have starting materials that should make this reaction run. I've got orange and I've got blue. Green should still be showing up. There's nothing endemic about this system where it got tired. Something else is wrong here, where you've added a material that's suppressing or hurting this reaction that was not there at the very beginning of the reaction, right? So this is where you can focus your studies on what's actually happening in the system. This is just the mass balance. So I took just the, I believe it's this one right here. And all I'm doing is summing every time point for the total amount of material in the system. So this is just a mass balance check where what I'm doing is taking each data point. Since you started off with 0.11 and 0.22, you should have a total mass of 0.33. And if we take each data point as visualized and sum it over time, I get this curve, which is my mass balance over time. If everything is good, that should be a straight line, right? And seeing the visualization like this allows you to see a certain curvature. You can see that mass balance at the very beginning takes a big dive and then it ends up into a flat point. It's not linearly, it's not drifting from mass balance equally over time. The mass balance takes a big jump at the very beginning that you're missing material, and then later over time it sort of falls into this point. What does that mean? Like, what I mean is your two options could be, if you just had this dying over time, it might look like just a straight line like this. You're always deviating from that. But instead, you've actually got this jump away from mass balance and then sort of a slower part.
The jump away is the fact that your A and B are combining into product rather than being, like it's not 1 plus 1 to 2 product. It's both of them combining into the one. So your concentrations there are going to sum to less than initial.
Yep.
But then later on it's the decomposition.
Exactly. So the way I set up this mass balance thing was probably incorrect. This trend right here is just equal to concentration A plus concentration B plus concentration product. That's all I did. And it looks like, well, wait a minute, I'm losing a lot of mass here, and then I go linear. But these two are being combined to this. The overall stoichiometry is 1 of this plus 1 of that equals only 1 product. So the mass balance equation I set up of just saying add doesn't reflect, there's nothing wrong with that. I'm expecting 1A and 1B need to disappear to make 1 product. So the true mass balance of the system, the way you could think about it, I only ever expect what 100% concentration of product based on my stoichiometry should be what? The maximum I could ever make. If this was the experiment I ran right here, how much product could I ever make in this system? Has to be your limiting reagent, right? So you need to adjust this equation to reflect that fact, right? So the other way to look at this is, so what do you think the correct, how could I, give me a correct expression that would actually reflect the true, or the, like, sort of called the corrected mass balance in the overall system?
A plus B plus 2B.
Yeah, exactly. Well, A plus B plus 2P, something like that, right? So you can say A and B plus, and I'm going to double the concentration of product just because I'm giving it that sort of weight. That helps to clean this part out. The other way to do it is divide these by 2, right? So A and B come together, divided by 2 gives you your overall component. Either way, you have to consider that, first of all, your limiting reagent is going to be a total cap. That's sort of a gut check to make sure that, you know, your mass balance is not going to be above that level. But one way or another, is take advantage of your stoichiometry that you're going to have to be in the system. Yep, that's right. Okay, so,
Sorry.
yeah, please.
Quick question on that. I might be totally making this up, but like, do you also have to account for the concentration of the intermediate with that?
If you had it, yes. If you knew the intermediate, then that would show up in here, and you'd have to use a similar, basically, imagine if A and B made an intermediate,
Right.
then intermediate makes onto product. If you had the concentration of the intermediate based on the system, it would still be A and B over 2, plus intermediate plus product would give you your total concentration all the way through the system, right? It's the same, it would have, because in that way, usually intermediate and product will be opposing each other with a 1-to-1 stoichiometry.
Okay, but I
Yep.
was wondering here, like that big drop, is it because
It could be
you're
intermediate.
populating intermediate?
It could also be that you're populating intermediates you're not seeing. The problem here is that, yeah, that it looks exacerbated just because you're putting equal weight to 2 materials, even though you're using it up. Yeah, you're right. That's the other part too. So, second part, this is fitting. You should have gotten something like this. If you take that mechanism and then you try to build that sort of that system, you should have got a fit that looks something like this. It depends on which particular starting material or which experimental run you use. But when you do a fit correctly, the things I wanted to point out, the measured values should show up as these hashes. So that's these values in here. Those are the values that you input as your experimental data. And then the values that it's fitting are usually represented as a different sequence. In this case, it's these hollowed lines. And if you let the thing run, it doesn't matter how many populations you use, it doesn't matter how many cycles you use. What you should see is that you'll get something that looks like this. It's kind of getting close, but you're not able to get the right curvature, you're not able to get the right overlap. It's your experimental value kind of agrees, but it's doing its best to sort of weight the two, right? And depends on which one of the 5 experiments you use, you'll see different deviations from that. I'm not going to go into a lot of other detail other than this is what it should look like if everything is running correctly. Yes?
On mine I ran it with all 5 experiments at once.
Yep.
Is that
You can.
what you're supposed to do? Or
Well, no, you can do them one at a time. If you do it one at a time, the problem you run into there is it's possible that the K values you get are non-unique, right? So you'll get a best fit K value, and it gets difficult to say what the individual orders or slow step would be from a one at a time. If you run all 5, it's going to try and find a single value. In this case, it would be trying to solve a single value for that K and that K that fits all 5 data sets. That's good. What probably, if you get a fit across that, because you're using 5 independent concentrations and 3 traces in each one, the K value you get is probably close to a true K-obs for that system, or at least the best overlap you can. Yes, so you can go through and do all 5. Kudos to you if you do. The thing I wanted to point out when I was reviewing some of your things that you handed in is some people got curves that looked like this. What's wrong here? This is a total fail. This did not work. Yes?
They didn't set the concentration of the initial data.
Yeah, what's happening here is your experimental data is down here. This is the fit value, and you see the initial concentration of all the species, your starting materials and your products, started out as 1. And that's because when you build the model, Capacity will just auto-populate and say, oh, you came up with new species, I'm going to assign it as a value of 1. So those initial values were just given as whatever value you put in as a default. And then what it's doing is it's best fit to try and say, well, I'm running your experiment, man. All I want to point out here is that, again, this visually is not an actual fit. It did nothing. It produced a graph. Getting a graph out of Capacity, you guys have played with language models. Models lie to you, right? Like just because it produced a value doesn't mean it's meaningful, right? So this is not an actual fit, and this is not set up correctly. Last one, how do you fix this? So we talked about this before, those features we went through. This is just going through, and I'm actually taking these last 3 data sets to really zoom in on them. So what I'm focusing on here is these 3. What's useful about them is they have a very large swing in the concentration of your initial starting condition. Why that's value is this last one right here corresponds to experiment number 5. That's a case where you've almost isolated it and you're focusing only on this B is dying over time, right? That's a case where basically it did nothing. There's almost no product available, and all you're seeing is B's decomposition over time, and that's where it comes back to what we discussed before. You have these really obvious parallel lines which is sort of associated with the rate of decomposition of that. Now, once you see them like this, you can see that there is a small maybe concentration dependence of B. As you drop to these very low levels, the ones that are in those kind of minus signs might be starting to flatten out a little bit more. But if you see those 3 solid parallel lines, it's because of it. You've identified a species where B is dying just because it's dying, right? This is an unstable component that's probably just, you've got some other reaction of B is turning into dead with a K value. And it's probably irreversible too, right? It's just a unidirectional reaction, not an equilibrium. If you saw, what I would say is, if you saw the same kind of stacking, but you're coming to sort of like a thresholding value, they're all kind of flattening out, even like experiment 5, if that sort of was to flatten out as is, it's possible that it's a deactivation, but maybe an equilibrium deactivation. You're reaching an equilibrium point rather than just I'm dying over time. And again, running it longer would tell you a bit more. But this is your first clue. Okay, but that doesn't express the other problem we said, right? The difference in concentration, the difference in product distribution, so our 2 green lines, this one here and these circles, so that one and this one, That comes to the difference in our two experiments where we said that the amount is changing based on the amount of catalyst is present. That's these two here. So the conversion was higher when we have more catalyst. So we need to add one more equation to account for the fact that catalyst had to die, right? So what do you guys want to do? What's an equation you could add to start to say, like, look, this reaction, if I have more catalyst, I can get to higher conversion. I know I'm killing catalyst over time. How do you want to add that feature to your model? You need a reaction that describes how catalyst is deactivating. Yeah?
I said B plus catalyst equals catalyst number 2.
Because, oh, like just dead catalyst? Like that, or?
It's sort of, in my model, I had B plus catalyst lead to something like catalyst plus B, which then reacted with more.
Oh, so you said B plus catalyst equals, call it int 2, and then that reacted with more B to make dead stuff.
That's, yeah.
Okay, what was your, again, at this stage, you don't have a lot of other information to do any sort of adjudication at all. Like, honestly, anything's on deck. I think the thing you have to get from the data you have, B is probably dying and it's doing it on its own. That it's having its own little dance party is one possible way, right? That's one potential outcome. And 2, catalyst has to die. So you have to have some way that catalyst is dying. And probably catalyst is dying is, basically, if you think of all the options you could do here, I need to kill catalyst. I could either kill free catalyst or intermediate, right? Those are my two choices. Yeah?
You could also just have the catalyst die on its own.
Yep, you could say catalyst is just like, catalyst is basically a panda and it just wants to die on its own, right? It's just, that's possible. What else? Yep.
Like catalyst reacting with like your dead B to
The-
do a dead catalyst.
Yeah, one other way to do this is, so B is turning to evil guy, right? And then that is reacting with catalyst to make dead catalyst, right? So, and again, at this point, what's nice about this phase, first of all, you can build each of these models, throw them and get your series of data, see does one fit better than something else. And I think for this data set, all the proposals that you put up here might actually fit equally well. With the data you have, you may not have enough information to adjudicate which one is right at that point. The better one, though, is now that you've got these are hypotheses. Give me an experiment that might help determine, like, let's look at these two. Option A, B turns into angry dude who then finds catalyst to kill catalyst. That's one possibility. And then possibility 2, catalyst just dies. Catalyst is a panda. Give me one experiment that might help you decide which of those two are your reality. Or 2 experiments, let's say. Yeah.
Run an experiment where you just have B
Yeah.
under the reaction conditions.
Yeah.
And see if you can isolate like a decomposition product.
Yeah, go hunting for the pissed off dude. Yep, that's a good one.
And then you could also do the same thing where you just have the catalyst, no A or B.
Yeah.
And see if it decomposes on its own.
Yeah, that's absolutely. Both of those are just like put them there and observe what happens. Put them in an MR and just watch the time course of those points, for sure. Let me phrase it, well, other ideas first before I yap out. I saw another couple of hands. Yeah.
Like first, like that kind of thing, like you could take the exact same reaction conditions, but put your catalyst in first, and then just like wait for a bit, and then see if like once you add A and B, it gives you the same.
Yeah, absolutely. So this is a time delay. Does that make sense? If I put catalyst in, do nothing, then inject A and B after 1 minute, 5 minutes, 12 minutes, an hour, I'm basically staggering my start time, right? So I'm allowing a catalyst to do something for some period of time under reaction conditions, and then I'm bringing in the rest of the party identically to all cases, right? So this is like a delayed action. So you're right. Looking for individual materials is absolutely your highest bar. Maybe it's from years being abused by this. I hate that answer just because there's so many times, it becomes Schrodinger's cat. There's so many times where go find that intermediate is like go find the Holy Grail, right? It's a fool's errand of like sometimes putting your hands on these weird decompositions is very, very, very hard to do. And I'm reacting as from years of reviewer 2 going, saying, well, if you're proposing this, go isolate that. And I'm like, F you, pal. You do that. part of the problem too is that usually with a time course like this, you did your best to measure stuff, is one way you can look at it. So the fact that I don't see something else building up might mean that whatever the heck I'm turning into is just invisible, right? It's just, my mode of analysis does not allow me to see what I'm forming, so I'm kind of screwed. So that's a hard ask. What I always like to adhere to, if I have these experiments, I at least trust I have the ability to watch the formation of my product. And I at least trust I have the ability to watch the rate of formation of my product. So use that as your assay. If I already have a way to watch green show up, and I believe I can watch green show up, change your reaction conditions using that formation of product as your litmus test. In other words, if I can start a reaction where I inject the catalyst into a mixture of A and B, so 0 time of mixing, I can watch product come in. Great. If I do the reciprocal, where I just let catalyst chill out, then bring everything to the party, I'm doing the same analytical assay. I'm watching product form for no more effort. I don't have to go hunt for a new material. I can use exactly the type of technology I have just to watch product build in, and I can compare the two. If I wait 20 minutes versus I wait an hour, and the rate of product kicking off once the party's brought together is identical, order of addition doesn't matter. It's not my little fuchsia box that catalyst is just dying. Yeah?
There's another option, which would be putting A and B together and then adding catalyst.
Yep.
And I think that would help you differentiate the purple very well, because if you let B just decay into the evil guy, then adding catalyst should just make the reaction not start at all.
Or again, you have a time series again. If you mix A and B, B is decomposing, and if you can watch what's happening during that time, you'll watch, kind of like that top orange curve, you'll see B is doing something while A is not doing anything. A is chilling out and saying, I'm ready to go, pal, and I'm not decomposing, and B is already sliding. So you're like, okay, I know B is doing something. If you start the reaction by adding catalyst right at the very beginning, no delay, versus I've let B decompose and then start the reaction, you've built up a certain concentration of evil guy, which then might be a fast deactivation. Absolutely. Yeah, please.
You could also just put B and catalyst together and know A and see how B changes over time.
Yep, that's a good one to check to see what your third proposal is. If B is endemic to catalyst death, you expose the two together, you watch how that behavior happens, but once again, the thing I want you guys to start thinking around is start changing this. These order of addition experiments are probably some of the most powerful ones you have, because you can start doing these authentic they become sort of these really good ways of saying, I can recapitulate or build a system that has some byproduct that I don't know what it is, and I can be reasonably sure that it's whatever its identity is common to the real reaction, but I have a little bit more control about where it's actually showing up. Right? I don't need to know what evil guy is. I just know that by putting catalyst and B together and I'm forming that evil guy, well, more time equals more of that material, and I can build a series of experiments where I'm slowly walking out the exposure time and proving that the longer that B and catalyst stick together, the more catalyst dies, for example, right? So in the end, that's what I built. I actually built, again, the data I gave you was based on this model where I had B dies, and then it forms evil guy. Evil guy reacts with catalyst to make dead cat. That's how I built it, at least right now. Yeah.
How viable is like taking the data that you already have and then building a model and then like proving that it fits better to say like, oh, this is my mechanism? Like, would that be enough?
That again, Jax, or it in one way, it does depend on this. I think there's some situations where you might need a bit more information, but in fact, that is the cycle. I have an experiment, I have a hypothesized mechanism. I run a series of VTNA where the language you want to use here is in the VTNA we have, the VTNA is consistent with the model where the A step is my turnover limiting step because I have an order in A, and the B step is fast. The second step of it, that is the true kind of system that we have. So that's the language you're proposing, is that I do have this core mechanism, that's okay, and in fact, the first step is slow and irreversible in my step. The fact that we have these other deviations means that we have to go back to our model, we add new steps, we rerun that experiment and say, given the 5 data sets I have and this new model, this is consistent with my expanded model, I get a better fit. Remember, with any of these ones too, that's probably, call that B+. You at least need to come that far where your new model, because you're modeling it, fits the data you have in hand. The single highest thing you should hold yourself to, though, is once you've got this, you can now propose a hypothesis and a new experiment, which then validates your model further. The final gold star is, once you've got this expanded model, predict an experiment which might help to validate or refute. The best would be is if you built 4 or 5 different models and each of them fit equally well with the data you had, the answer is come up with another experiment that would actually allow the two to differentiate. There may be a case where, and I didn't run it through there, I didn't actually think of the catalyst, the one that you suggested. B plus catalyst makes weird dye, which picks up another B. That actually might do a pretty good job with the concentrations you have here. So you might have a case where you propose 2 models which fit better than your initial, but equally good, which means now come up with something else that says if I perturb, let's say, catalyst concentration or delay time or something else, I might need another experiment to differentiate between those. That's the sequence. Again, this is the part that I really, really like about this part. Okay. Any other questions on that? Cool. I expect you guys are going to be awesome at this because next week you're going to have your take home to go play with this. As a quick warning in advance, what I'm going to give you guys, and again, if you need more time, let's play it this way. I will release you guys the midterm on Sunday, Monday. You'll have a week to complete it as much as you want. If you guys are finding that you're time compressed because of other things and you need sort of hands up another week, no problem. I just wanted to try and get this done so that you could hand it in and be done over midterm break. If you find that you need more time to sort of focus on whatever I provide you and you say, give me another week, that's fine. Just send me an email. There's no issue on that. The one that I will flag, though, is I'm going to give you sort of treatments and stuff based on what we've discussed here in class. I'm going to ask you to go find a literature paper individually, your own, and do the data treatment on this, which means everybody's going to have to find a paper that uses VTNA and go and do the interpretation of that. I'll show you guys how to do some data extraction so you can actually use published data in this way. Has anybody ever played with what's called OCR data extraction from graphs? If anybody's published any graph, let's say this is a common one, somebody puts in a paper somewhere and says, oh look, here's this awesome graph and it's a picture in a JAX paper. But let's say I want to play with your data, but you did not publish your data series. There are some awesome tools that let me take that picture and at least estimate what the numerical values of these ones are and go from a graph back to an Excel sheet. Has anybody ever done that? Okay, I'll post a couple. They've gotten much, much better. But me and Jordy used to have to do this all the time where somebody would publish data and we're like, hey, I want to work with your data. Could you share it? No. Okay. Now I've got your data. But no, it's a really, really useful thing to do. So again, I know that that's a consequence. A lot of people that publish their thing will not give you the primary data. I'll show you a way that you can extract it directly from the graphs is a good enough one to complete the assignments. All right, I will see you guys on Wednesday.